So let me quickly recall a few notations from the last lecture and then proceed with those notations. Yes. We introduced script M as collection of all subsets of R that are Lebesgue measurable. Let me remind you what is measurability. That is collection of all those subsets of R for every test set A. You will have measure of the test set is equal to measure of part of the set in E plus part of the set in E complement. And we observe that script M is a sigma algebra. We observe that script M contains all intervals in R. I, the collection of interval, is contained in M. Script I is contained in. Once it contains open interval, it should contain all open sets, being a sigma algebra. In fact, it contains all closed sets as well, being a sigma algebra and being closed under complementation. It is closed under countable union, countable intersection, and so on. Therefore, M will contain G delta sets, F sigma sets, F sigma delta sets, and so on. Thus, the sigma algebra contains intervals, open sets, closed sets, G delta sets, F sigma sets. Okay. So we feel that M contains lot of subsets of R. Okay. On the other hand, we can think of smallest sigma algebra containing all open sets or all open intervals. Okay. And that we called as script B, called Borel sigma algebra. Let B be the smallest sigma algebra containing all open intervals. Or you can say containing all open sets. Then clearly you have called Borel sigma algebra. Then one obvious thing is that script B is contained in script M, and both are sitting inside power set of R. And how does it follow that B is contained in M?
B is the smallest one, that's why.
P is the smallest sigma algebra containing open intervals or open sets, whereas M is known to be a sigma algebra containing all open intervals. Therefore, definitely the smallest one will be contained in the other sigma algebra. Now, one question. How do you know that a smallest sigma algebra containing open set exists? I think I have commented on this as well.
2 to the power r.
No, I am asking you, how do you know that a smallest sigma algebra containing all open sets exists? Sigma algebra containing all open set exists is clear. 2 power r is a sigma algebra containing all open sets. And in fact, we know M also is a sigma algebra containing all open sets. So existence of sigma algebra containing all open sets is clear. Question is, how do you know a smallest sigma algebra containing all open sets exists?
By taking intersection of all such
Yes. We remark
sigma
that,
algebras that contains.
yes, you are right. We remark that intersection of sigma algebra is again a sigma algebra. Okay. Therefore, you consider all possible sigma algebras containing open sets. For instance, 2 power r, for instance, script m, and so on, and take their intersection. Okay. Then you will get the smallest sigma algebra containing all open sets. Therefore, existence of B is based on the fact that intersection of sigma algebra is again a sigma algebra. Okay, so these are few things that we have commented. And next, we would like to see whether this M, the sigma algebra containing all open interval, can exhaust 2 power r. Can it be exactly equal to 2 power r? Okay. We already saw one argument to convince that script m cannot be equal to entire 2 power r. Okay. The argument was as follows. We proved that Lebesgue countermeasure m star, which acts from power set of r to 0 infinity, is not countably additive. On the other hand, Lebesgue measure m, which is equal to m star restricted to script m from script m, the collection of all Lebesgue measurable set to 0 infinity, is known to be countably additive. So the original function m star is not countably additive, whereas its restriction to script m is countably additive. These two facts should give you that. Can you complete?
Script m is not equals to 2 to power r.
Therefore, script m, the collection of all Lebesgue measurable sets, is not equal to 2 power r. That is, script m is properly contained in 2 power r, or that is, there are subsets of r which are not Lebesgue measurable. That is, there are sets in R which are not Lebesgue measurable. Or I should say, there is at least one subset. Why should I say there is? There is a subset of R which is not Lebesgue measurable. Okay. So in this way, script M is properly contained in 2 power R. This seems to be an indirect way to convince that script M and 2 power R are 2 sigma algebra that do not match exactly. As I told you, our next intention is to see that there are Lebesgue measurable sets which are not Lebesgue measurable, sets which are not Lebesgue measurable in a more straightforward way, relatively straightforward way, I should say. Okay. So now let me give you an example of non-measurable set. A non-measurable set. Existence of non-measurable set we have guaranteed in this way. M star is not countably additive on 2 power R, whereas its restriction is countably additive on script M, and this shows that M and 2 power R cannot match. So in that way, we are sure there exists a non-measurable set. But now what we want to do is to see in a more straightforward way an existence of non-measurable set. But I should say that it's not as straightforward as you think. Okay, we are going to invoke axiom of choice. If you remember, in proving M star is not countably additive also, we invoked axiom of choice. Yes or no?
Yes, sir.
Yeah.
Yes, sir.
So this is a slight modification of the proof that we have done for M star is not countably additive. Okay. But at least that will tell you, yes, here is an example of non-measurable sets. Okay, this is an example of non-measurable set. So having said that, now let us try to get a concrete example. What I will do is the following. Let me start with the open interval 0, 1. Let I is equal to not open interval. It doesn't matter if you take open interval or closed interval or half open, half closed, and so on. So let me work with this. I is equal to closed 0, open 1. First and foremost thing that you can observe is that then I is measurable and its Lebesgue measure is 1. Okay. Note that intervals are measurable. Therefore, I is measurable. I is Lebesgue measurable. And Lebesgue measure of I. Once it is measurable, I can talk about M of I is equal to 1. Okay. In order to get an example of a non-measurable set, I am going to define an arithmetic in I. I am going to take elements in I and I am going to add them. But the outcome after adding, the result, again I want to be in I itself. I don't want to leave I. I don't want to go outside I. So basically, I am going to define the so-called addition modulo 1. Okay. For x comma y in I, define the following. Define. The notation that I give is as follows. X addition modulo 1 y. X plus circle y. Okay. How do I define? Note that when x and y are in I, x plus y can range between 0 and 2. 2 not including. X plus y in general can range from 0 to 2. In case x plus y is less than 1, then I will keep as it is. So I will define x new addition y or circle addition y as x plus y if 0 is less than or equal to x plus y is less than 1. The moment it goes outside 1, I will pull it back to y by subtracting 1. So I will define x plus y minus 1. If x plus y is greater than 1, but in fact it will be less than 2. Okay, so this is the definition of addition that I have in I. In fact, this is what is called as addition modulo 1. You can note that then, though it is not relevant to us, let me just record that. Then this new addition is a commutative associative operator and associative operation. Okay, defined on I. Taking I would request all of you to mute unless you really want to speak. It's a commutative and associative operation taking pair of numbers or elements in 0, 1 into number in 0, 1. It will take 2 elements in I, it will add, and after adding, the outcome is again in 0, 1. Is that clear? The addition is clear. It is addition modulo 1. Okay. If you want to view it in a slightly different way, what you can do is the following. Okay. You have 0, 1, and you have a number x. Okay. Identify this number x with 2 pi x. Okay. For each x in 0, 1, you assign 2 pi x and consider this 2 pi x as an angle. 2 pi times x. I repeat, each element x in 0, 1, you assign to 2 pi x and you think 2 pi x as an angle. Okay. Now, can you interpret what is addition of x and y means? Adding y to x is same as adding the angle 2 pi y to 2 pi x. That means you are rotating again this ray by an amount 2 pi y. Yes or no?
Yes, sir.
Addition of y with the x is same as addition of 2 pi y angle to 2 pi x. That means you are rotating this further by an amount 2 pi y. Okay. And if you complete one round, we again come to the original. Right? That's what we mean by modulo 1. If you go outside 1, you come back. The subtraction by 1. So here it automatically will happen. Once you complete one round, you will come to the original. Okay, there's this 2 pi round corresponds to addition modulo 1. Okay, there is another way to look at this addition. Anyway, so hoping that this arithmetic is clear, now let us proceed. Let E be some subset of the set that we have taken, namely 0, 1. And let me fix an element y from 0, 1. Y is arbitrary but fixed. Be fixed. It's an arbitrary but fixed element. Now, using the arithmetic that we have defined between 2 points, now I am going to define translation E with y. Ordinary translation you already know. E plus y is equal to E plus y. By definition, it is set of all x plus y such that x is in E. This you know, but now I am going to define a new translation, special translation, defined via this special addition. Let us define E, define a special translation. You can very well guess how should we define E plus y.
Yes, sir.
E plus y, E circle plus y is equal to x circle plus y, x in E. Okay, so this is my definition. What is E? E is an arbitrary subset of the interval I that we have taken. Now, before proceeding, we need to observe certain preliminary things about this new translation. Okay, we shall have some preliminary observations. So I will put that observation maybe in terms of, let us say, a lemma. And the content of the lemma is as follows. If E subset of 0, 1 is a measurable set, then the new set that you have defined via special translation, that is E circle plus y, is also measurable. Not only that, and the measure of translated set is equal to measure of the original for every y in 0. Okay. Please bear in mind that we have not proved this. We have proved only for ordinary translation, or we have remarked only for ordinary translation. If E is a measurable set, E plus y will be measurable, and measure of E plus y would be is equal to measure of E. If it is ordinary translation, but here we have special translation. Okay, so this we will try to prove first and then proceed. Proof. As you can anticipate, the main step would be to connect the special translation with ordinary translation, because we already know that ordinary translation is measure invariant and ordinary translation set are measurable. Okay, so we will try to connect special translation circle plus with the ordinary plus. Let y element of 0, 1 be fixed So how do we connect? For that, let me define two sets. Define E1 is equal to E intersection closed 0 open 1 minus y, and E2 is equal to E intersection 1 minus y open interval 1. Okay. Do you see that E1 and E2 are disjoint?
Yes, sir.
Obviously, E1 is inside
Yes, sir.
the interval 0, 1 minus y, and E2 is in the other part, 1 minus y 1. So E1 and E2 are disjoint. Do you see that E1 and E2 are measurable?
Yes, sir.
Yes, sir.
Hypothesis of the lemma is that E is measurable. And we know that intervals are measurable. And we know that measurable sets form a sigma algebra. And therefore, intersection of two measurable sets are measurable. Okay. And do you see that union of E1 and E2 is E?
Yes, sir.
So let me write all
Yes,
this.
sir.
Therefore, let us note down all these things. Therefore, E1 and E2 are disjoint measurable sets. Therefore, then would be better. Then E1 and E2 are disjoint measurable sets whose union is E. You can easily convince yourself with this statement. So what? Therefore, measure of E is equal to measure of E1. You know that measure is countably additive plus measure of E2. Okay, so this is an observation. Our primary purpose is to relate the translation invariant, the special translation with ordinary translation. Okay. Now, let us try to see E1 special translation with y. What is E1 plus y? What will you do? You will take an element in E1 and you will add to y. But remember, elements in E1 are less than 1 minus y. Therefore, if you add y, it will be less than 1. And if it is less than 1, our addition says that it is ordinary addition.
Yes, sir.
So, E1 special translation y will be same as
X plus Y.
not x plus y,
E1 plus
E1
Y.
translation y,
Relation Y. Yes, sir.
ordinary translation.
Yes, sir.
Is that clear?
Yes, sir.
And
Yes.
so what? And so E1 special translation y is measurable. Is measurable. And measure of E1 special translation y is equal to measure of E1 plus y ordinary translation, and it is measure of E1.
E1.
Because we know that measure is ordinary translation invariant. Okay. Now, what about E2 special translation y? Remember, E2 elements in E2 are greater than 1 minus y. So if you add y with it,
It is greater
the
than.
elements will exceed 1.
Yes, sir.
Once it exceeds 1, you should pull back to I by subtracting 1.
Yes, sir.
Okay. Therefore, E1 special translation y, sorry, E2 special translation y will be, can you tell me?
E2 plus Y
Plus
minus 1.
Y
y
minus 1.
y minus 1. E2 plus y minus 1. Ordinary addition you will do, then you will exceed 1, then you have to subtract 1. So E2 special translation y is same as E2 translation with y minus 1. And so what? And so E2 special translation y is measurable. Is measurable.
Yes, sir.
And measure of E2 plus y is equal to measure of E2 plus ordinary plus y minus 1, which because of translation invariant is measure of E2. Okay.
Yes, sir.
Now, I claim that this claim I will not prove. It is easy to prove, so please do it. But E special translation y is same as E1 special translation y union E2 special translation y. That will follow from the fact that E is E1 union E2, and also with the help of this arithmetic that you have defined and so on, you should be able to see this. E translation y is same as E1 plus y and E2 plus y. Now, plus I mean or special translation. Further, the sets E1 plus y and E2 plus y, special translations, are disjoint. Okay. And E1 special translation y and E2 special translation y are disjoint. Okay. They are measurable, you have already seen. So you will get that E plus y is also measurable, being union of two measurable sets. Okay. Also, E plus y is measurable. Special translation of E with y, which is union of special translation of E1 with y and E2 with y, and E1 with y and E2 with y are measurable, therefore union is measurable. And further, measure of special translation of E is equal to measure of special translation of E1 because of countable additivity plus measure of special translation of E2. Do you get me? What is missing is only
Yes,
this
sir.
part. E plus y is equal to E1 plus y union E2 plus y. That is an exercise. It's a direct verification. So I don't want to enter into it. And this we have seen that measure of E1 special translation of y is same as measure of E1 plus y because they are same. Measure of E2 plus y minus 1. And this is measure of E1. And the second one is measure of E2. And E1 and E2 are disjoint parts of E. Okay. And therefore, measure of E1 plus E2 is measure of E. Thus, the lemma. If E is measurable, then special translation of E is also measurable and the measures will match. Okay. So this proves the lemma. We are yet not ready to give an example of non-measurable set. We are just gathering the background works. Okay. Now, as I told you, the main idea will be axiom of choice. And for axiom of choice, you need collection of sets and etc. etc. So I am going to start from an equivalence relation. We define x related to y if and only if x minus y is a rational number. Same thing we did when we proved m star is not countably additive. So we start with this equivalence relation. Then star or a delta is an equivalence relation. So I am defining this relation on I. Okay. For we define x related to y if and only if x minus y in Q for every x and y in the interval we started with, namely close to 0, open 1. So on I have an equivalence relation. And what is fundamental thing about equivalence relation?
The partition.
Partition classes.
We will get equivalence classes, and equivalence classes forms a partition.
Partition of set.
Yeah. Then we get equivalence classes. I will not write the definition, etc. We have seen this. Equivalence classes, this thing, and distinct equivalence classes form a partition of the parent set or underlying set, partition of I. Okay. So now you have collection of sets. It should remind you axiom of choice. Now I can form a new set by selecting exactly one element from each of these distinct equivalence classes. Okay. And that I am going to call as P. Now, using the axiom of choice, there is a set. Of course, it will be inside I. There is a set P which contains exactly one element from each equivalence class. So is it clear about what is P? You have collection of equivalence classes. Basically, they are set. You select one element, exactly one element from each of this set and form a new set. That is P. We will show that P is non-measurable. We will show that, and that will give an example of a non-measurable set. We will show that P is non-measurable. For that, what we will assume that P is measurable and get a contradiction. Okay, but we need some more things to reach at that level. We shall assume P is measurable and reach at a contradiction. But before doing that, we should do a few more preparatory things. But we need to do a few So finally, I will prove that P is non-measurable by assuming P to be measurable and getting a contradiction. Okay, so we are not in that stage now. So what I do is the following. Let sequence be an enumeration of rational number. Enumeration of rationals. You know that set of rational number is countable, so you can arrange it as a sequence. Not all rational numbers in the interval 0, 1. With, I will put R0 as 0. R0 is 0 and the remaining rational numbers are listed. R1, R2, R3, and so on. Okay. Is that clear?
Yes, sir.
It is an enumeration. But can you, though it is not relevant to what we want to do, can you list it in increasing order? Can you list the rational number in increasing order? R0 less than R1, less than R2, less than R3, and so on. Can you do that? You cannot, because
sir.
between any two rational number, again there exists a
Rational number.
rational number. So you
Irrational.
cannot list it in increasing order, okay? But it is countable, therefore you can list it. You can list it.
Yes, sir.
But I will make that list as R0 to be 0. And I am not bothered how R1, R2, R3, etc. So don't confuse. When I say I can list it and make R0 as 0, that doesn't mean that I can list in increasing order. That is never possible. Because between any two rational, there exists another rational. Okay. Anyway, that is not relevant to us. So we have Ri. Now what we do is define new sets. Pi. P is already defined. Is equal to P, which we got from axiom of choice, plus Ri, where plus stands for our special plus. I is equal to 0, 1, 2, and so on. Okay, so you translate this set to P, which we got from axiom of choice, with the Ri using special translation. Thus, you have now countable collection of sets. Okay, now I am going to note a few things about this Pi. Okay, some observation. First observation is that P0 is, you have to complete. Observe. What is P0?
It's P itself.
P itself.
P. It will be P. It is trivial. Now, second observation is the following. Plain PIs are distinct. PIs are distinct. How do we establish this claim? It's easy, but let me do it for the completion. We will assume that PI intersection PJ is equal to, is not equal to null.
Fine. Non.
PI intersection PJ is not equal to null set for I not equal to J. And let us try to get a contradiction. But keep in mind how we defined P. P is obtained by taking exactly one element from each of the equivalent class. That you should keep in mind. Let X is in Pi intersection Pj. Okay. Suppose such an X is there. That will imply X is in Pi and obviously X is in Pj. Now, what is the meaning of X is in Pi? X will be an element in P, special translated with Ri, right?
Yes, sir.
That implies X is equal to some small Pi plus Ri, where Pi is in P, Pi is in P, and X is equal to some small Pj, special translation with Rj, where small pj is in P. An element is in capital Pi means it is an element in P, special translated with the Ri. I am using that definition, that's it. And that implies Pi translation Ri is equal to Pj, special translation Rj. Okay. And this should give. Now apply the definition of special translation. Either it is same or you have to subtract one. In whatever case, you will get Pi minus Pj to be equal to Rj minus Ri. And Rj and Ri are rational, and therefore the difference is rational. Okay. So Pi minus Pj is rational, and that gives you what? Pi is related to Pj.
Yes, sir. They are in same class.
Can it happen You are taking two elements
No, sir.
from P. Okay.
No, sir.
And P contains exactly one element from each class. So this will tell you that since P contains exactly one element from each equivalence class, this is possible only when I equal to j. We get I equal to j. Thus, you cannot find a common element x if I is not equal to j. So that proves that PIs are distinct. Another observation about PI is the following. Claim also that the interval 0, 1, that was the ambient space which we work with, is equal to union of all PI. And out of this equation, one side inequality is trivial. Each PI is contained in 0, 1. Therefore, union I PI is contained in 0, 1. So I have to prove only the other way inclusion. 0, 1 is contained in union I PI. I have to prove. For this claim, let x is in 0, 1. I have to prove that x is in union I PI. Okay. Now x is in 0, 1, and you know that the 0, 1 is being partitioned into equivalence classes. Therefore, x will be in one of the equivalence class. Okay. That implies x is in one of the equivalence class. And how did you make P?
By choosing one element from each class.
Each class. Therefore, this x will be equivalent to some element in P.
Yes, sir.
Because P contains
Yes, sir.
one
Yes,
element
sir.
from each equivalence class. So x is in one of the equivalence classes, and so it is equivalent to, when I say equivalent, related, I mean equivalent to some element in P. Because P contains representative from each equivalence class. Now, what is the meaning of saying x is equivalent to some element in P? How did you define equivalency? X minus y is a rational number. Therefore,
Yes.
x is
Rational number.
equivalent to some element in P means x minus an element in P is a rational number, right?
Yes.
X differs from an element in P by a rational number. By a rational number. So what? So did you get x is in Pi?
Yes, sir.
What is Pi? An element in P plus Ri, right? Yeah. So that implies x is in Pi. X differs from an element in P by Ri, means x is in Pi, which is defined as P plus Ri. Maybe you need to think a little bit on this. Okay. But this is the idea. So thus, the claim is that closed 0, 1, open 1 is union IPA. Okay. Now we are in a stage to prove that P is non-measurable. Okay. Now, if P is measurable, let us start with the contradiction. Suppose P is measurable, then what we get?
Excuse me, sir.
Yes.
Sir, X differs from an element in P by rational numbers, but P contains one element from each PI.
I told you, that is why I told you this may need a thinking. You please do it. Okay. So this part, I made a clever statement here. This may need a rethinking, and so I will leave this plain. This is the rough idea. Okay, to prove that closed interval 0, open interval 1 is union IPI. I don't claim that I have proved it in all detail. With these ideas, try to prove that closed interval 0, open 1 is union IPI. Okay, I will not enter into the detail, but you can do. This is the basic idea. With this basic idea in hand, you try to prove that closed of 0, open 1 is union IPI. Okay. Polish this to get the claim. I can't do it, but it is unnecessarily taking time and it is deviating from what we want to do exactly. Okay. So these are all some minute details which you should try to do. Now, if P is measurable, then what we will get is the following. Measure of 0, 1. Assuming that we proved 0, 1 is equal to union PI, this is equal to measure of union I PI. Okay. Yes or no?
Yes, sir.
Yes.
And
sir.
what is PI? How do you define PI?
PI is a distinct
Just
class.
in
That's
the
okay.
equivalence classes.
It is P translated with RI,
RI.
right? And you have seen that measure of P translated with RI is same as measure of P, the lemma you proved. Okay.
Yes, sir.
So this will be summation I measure of PI, because PIs are disjoint and so on. And that is equal to summation I measure of P. Okay. So now, if measure of P, I don't know what is measure of P. If measure of P is 0, you will get summation I measure of P is 0. Okay. If measure of P is equal to 0, we get summation I measure of P is 0. And that will give you, that is, measure of 0, 1 is equal to 0. That's not possible. Now, if measure of P is non-zero, if measure of P non-zero means it will be greater than 0. Maybe infinity, but it is greater than 0. But infinity cannot happen because you are inside a closed 0, open 1. Anyway, if measure of P is non-zero, what can you say about this summation? A non-zero number, you are adding infinite number of times.
It is infinite.
Can it converge?
No.
Then summation I MP is not convergent. Or you can say it is equal to plus infinity in this case, because each one is positive. Okay. And again, you get a contradiction, but because left hand side is measure of 0, 1, and measure of 0, 1, you know that it is
1.
1.
Yeah. So in both cases, you get a contradiction. Thus, both cases led to a contradiction. Both cases lead to a contradiction. What does it mean? Our assumption is wrong. Why contradiction is clear, right? Because left hand side is a finite number 1, whereas right hand side is either 0 or it is not finite at all. Therefore, P is non-measurable. So you got a non-measurable set. And this proves our claim. There exist subsets of R which are not measurable. And in fact, we got a subset of closed 0, open 1 itself. Okay. Thus, M is strictly contained in 2 power R. There are non-measurable sets, is clear now. But unfortunately, it is not a construction. It is actually like an axiom of choice. I'm not giving you what is P. Everything is based on the assumption that axiom of choice is true. Okay, anyway. Now, I want to talk a few things about the cardinality. You have seen lot of examples for measurable sets. Yes or no?
Yes.
Whatever
Yes.
subsets, usual subsets of R you come across, intervals, etc., complement of intervals, union of intervals, intersection of interval, etc., all are measurable. And with some involved work, you could also prove that there exists some non-measurable sets. Right? There exists plenty of measurable set. I can give many examples. And there exists some non-measurable sets, which we proved, of course, with some labor. That's okay. So what these two things, if you compare, what do you feel? If you compare number of measurable sets and number of non-measurable sets, what is your feeling at the first sight? Which will be more?
Number of
Measurables.
Measurable sets is more, looks like, okay. A non-measurable set is very hard to construct. We did with much work, okay, but that is not the case. Okay? But that is not the case. It is something like, you know that almost all functions that you come across is differentiable, or it is differentiable at least at some points. And you might have seen only very few examples of non-differentiable function. When I say non-differentiable, it is differentiable nowhere. Okay. Have you seen examples of nowhere differentiable functions?
Yes, sir.
One example can you give? Nowhere differentiable functions.
Yes, sir. F of x equals to 1. X belongs
No,
to
there is
Q
some.
and-
No, you don't have to give the expression. Weierstrass function. Have you heard about Weierstrass nowhere differentiable function? Okay. Anyway, so the point is not that. You might have constructed non-differentiable function with involved work, and you might have seen only very few examples of non-differentiable function, like Weierstrass functions and things like that. But you have seen plenty of examples of functions which are differentiable at least at one point. So a natural feeling will be that the number of functions which are nowhere differentiable is much less than number of functions which are differentiable at least at one point. Any function you take which comes in practice, sin x, cos x, mod x, all are differentiable at some points. Even mod x, it is non-differentiable only at one point. Okay, I am talking about functions that are differentiable at least at one point. So functions that are differentiable at least at one point is more in number compared to functions that are nowhere differentiable is our feeling, but that is not correct. I don't know whether you have studied category theorem, Bayes category theorem. Have you heard about category and so on in a real analysis?
Yes, sir.
So one of the application of Bayes category theorem is that the collection of all functions that are nowhere differentiable is second category. Nowhere differentiable function is second category, and collection of functions which are differentiable at least at one point is first category. Okay, and therefore in categorical sense, the differentiable functions are less in number and non-differentiable functions are more in number in the sense of category. It's of course counterintuitive. It is beyond our intuition, because every set that we come across are differentiable at least at one point. But to be precise, knower differentiable functions are more compared to differentiable functions or functions that are differentiable at least at one point. When I say more, I mean in the sense of category. The functions which are differentiable at least at one point forms only first category set, whereas functions that are knower differentiable forms second category set. Okay, and first category set are called meager set. Meager. Have you heard about that word? Meager. It's a mathematical term, but if you see the literal meaning of meager, English meaning of meager, it is that, I don't know whether this or this, you can find out. I think it is second one. Okay. Anyway, meager, the literal meaning is that it is negligible. It is negligible. So first category sets are negligible, whereas second category sets are like prominent sets. Okay. So these things are just, I told you to review real analysis. So just something is hard to see and something you have plenty in your before your eyes doesn't mean from that you should not go to a wrong conclusion. Okay. Differentiable function you can see plenty in number, whereas non-differentiable function, in other words, knower differentiable functions are very few that you have seen. That doesn't mean that knower differentiable functions are really few. Similarly, measurable sets are plenty in front of your eyes, and non-measurable sets you have constructed with much involved work doesn't mean that there are more measurable sets than non-measurable sets. That conclusion you should not make. Okay, is it clear what I am saying?
Yes, sir.
Yes, sir.
Yes,
Clear.
sir.
Now let me make things more precise. I wanted to talk about cardinality of measurable sets, cardinality of 2 power r, cardinality of non-measurable sets, etc. etc. Okay. So let us quickly review certain few things from cardinality. Again, basic real analysis. If things are finite sets, your life is simple. You have to just count number of elements in the sets, and if number of elements are same, they have same cardinal number. But
Yes, sir.
issue comes only when you have to deal with infinite sets. Okay, so how do you compare two infinite sets, sizes of two infinite sets? Okay, so let us quickly recall that and then go back to the cardinality of m, cardinality of 2 power r, etc. Okay, how to compare size of two sets. Let us quickly recall. One fundamental notion that helps to compare sizes of two sets are numerically equivalent. Okay, so let me define what is numerically equivalent. Two non-empty sets x and y are said to be numerically equivalent if there exists a 1-1 onto map from x to y. If there exists a 1-1 mapping of x onto y, not into, onto y, then we say x and y are numerically equivalent. Okay, so suppose you have x and y as non-empty finite set, then this can happen only when number of elements in x is equal to number of elements in y. Yes or no?
Yes, sir.
So
Yes,
numerical equivalence is something like keeping track of number of elements. Okay. Note that if X and Y are non-empty finite sets, then they are numerically equivalent. They are numerically equivalent if and only if they have same number of elements. So in this sense, numerical equivalence may be treated as extension of having same number of elements. So it is the concept we require for dealing with infinite sets. Okay.
yes, sir.
Now, number of elements in countable set. When I say countable, here I mean countably infinite. Okay. Denumerable set is given by a special notation. I don't know whether you remember it or not. Number of elements.
Let not.
Number of elements in a countably infinite set. Countably infinite set will be equivalent to n, numerically equivalent to n. Okay. Every sequence will be numerically equivalent to n. Number of elements in a countably infinite set is denoted by, do you remember?
Yes, sir.
What is the
Aleph
notation?
naught.
Aleph naught. Aleph naught. So every countably infinite set is numerically equivalent to each other, and they are all numerically equivalent to set n of natural numbers, and we regard its cardinal number as n naught, the Aleph naught. Okay. So now if you see, you have cardinal number 1, a set with one element, 2, 3, etc. And also you have cardinal number Aleph naught, n naught. Okay. This Aleph naught is Hebrew letter. Okay. Anyway, so thus we have cardinal numbers. One, 2, 3, etc. And also we have cardinal number Aleph naught. Okay. Now next what we want to do is we want to compare two cardinal numbers, m and n. Suppose that m and n are two cardinal numbers. Finite or infinite, I don't bother. Maybe 1, 2, 3, etc. something, or it may be n naught. Finite or infinite. This is just to scratch the surface. I will not go into the detail. We say those who feel an itching should consult Halmos set theory. Okay. I don't know whether you are familiar with that book. It is a wonderful book, Naive Set Theory by Halmos, P.R. Halmos. Okay. We say m is less than n to mean the following. What is the meaning of the notation m less than n? Remember now m and n are cardinalities of two sets. Okay. If X and Y are sets with m and n elements, m and n need not be finite. Okay. M and n elements, that is cardinality as m and n. Then we say m less than n if there exists a 1-1 mapping . From x into y, and there does not exist, there does not exist a 1-1 and onto map from x to y. Suppose there exists a 1-1 mapping from, these are all very clear if you consider the finite case. If there exists 1-1 mapping from this, but not 1-1 and onto map, then you say that m is strictly less than n. Okay, so that is our notation. Okay. Now, with these things in hand, you should be able to say that cardinality 1 is strictly less than cardinality 2, is strictly less than 3, and so on. Everything is less than Aleph naught. And what is Aleph naught?
Cardinality of n.
Cardinality of a countable set. Or
set.
that's true. Cardinality of a countably infinite set. Now let us go to uncountable sets. For instance, R or closed interval 0, 1, whatever it is. And I think you know a simple use to denote cardinality of uncountable sets. That is C.
Continuum.
C, set continuum. Okay. The symbol C, is used to denote number of elements or cardinality. Cardinality of R or any set which is numerically equivalent to R. Which is numerically equivalent to R. Okay. So C is called continuum, cardinality of continuum, cardinal number of the continuum. Whenever a set is numerically equivalent to R, then we denote it cardinality by C. So now you have the hierarchy 1 less than, cardinality 1 is strictly less than 2, is strictly less than 3, etc. Strictly less than Aleph naught. Aleph naught is for countable and C is for uncountable. So this is less than C. You cannot find a 1-1 onto map between a countable set and an uncountable set. Okay. So it is N naught is strictly less than C. But you can find a 1-1 map. So N naught is less than C as per the notation we introduced. M is less than N if. So this is our hierarchy for the time being. Now a natural question is whether there exists some cardinal number between N naught and C. Is there a cardinal number between Aleph naught and C? Do you know that answer?
Not exist.
No, sir. That does not exist.
That is called the Cantor's continuum hypothesis. Okay. Cantor's continuum hypothesis is that there does not exist a cardinal number between N naught and C. Okay. Now I have to say one more thing and then finish this review of cardinality and go back to our set M and 2 power R. So now you have a chain and you have seen that there is no cardinal number between N naught and C. So the next question is whether it stop at C or you can have again some sets with cardinality greater than C. Okay, greater than C. So next question. Are there any infinite cardinal number greater than C? The cardinality of
Yes, sir.
answer is yes. And how does it follow? It follows from the fact that a set X and its power set cannot be numerically equivalent. Okay.
Yes, sir.
So I will write that also. Towards this question, towards the above question, we have the following. Cardinal number of X is strictly less than cardinal number of its power set. You can find a 1-1 mapping from a set to its power set, but you cannot find a 1-1 onto mapping from a set to its power set. Okay. And therefore, 1 less than 2 less than 3 less than etc. Then you get Aleph naught. Aleph naught less than C. In between Aleph naught and C, there is nothing. That is continuum hypothesis. And then between C, after C, you have 2 power C. What is 2 power C means? The cardinality of power set of R. Or power set of any set which is numerically equivalent to R. And then you have 2 power C, its power set, and so on. Okay. And again, by extended continuum hypothesis, there is no cardinal number between C and 2 power C. After C, it is exactly 2 power C. There is no cardinal number. Again, that is continuum hypothesis. Okay. So this is the hierarchy of cardinal number. And you have one kind of countably infinity. That is Aleph naught. And you have infinite number of uncountable cardinal numbers. C, 2 power C, 2 power C, and so on. Okay. I repeat, 2 power C is used for denoting cardinal number of power set of R or power set of any set numerically equivalent to R. Okay. Now with this, as I told, this is only tip of the iceberg. If you wanted to learn more about cardinal numbers, it will take months, I would say. Okay. It's very abstract. It is very abstract. Even continuum hypothesis, whether it is true or not true. Have you read about that? I think Gödel has proved that continuum hypothesis cannot be proved. And another mathematician proved that it cannot be disproved. It cannot be proved, it cannot be disproved. That doesn't mean that it is true or false. So that's why it is taken as axiom. Okay. It's too abstract, so let us not go into the details. Okay. Anyway. Now, with all this background, let us go back to our concern, namely m, 2 power m, etc. Now, look at m, which is contained in 2 power r. What is cardinality of 2 power r? Cardinality of 2 power r.
C.
C.
2 power C.
2
2 power C. It is greater than C. Okay. It is not C. It is greater than C. 2 power C. Okay. Now I want to see what is cardinality of m. Cardinality of m. How do I do that? Of course, it will be less than 2 power c. That is clear. Clearly, less than or equal to, I mean, cardinality of being a subset, right? Cardinality of M is less than or equal to 2 power c. Do you know an example of a set which is set theoretically big but measure theoretically small? Cantor set. Okay, it is uncountable but outer measure is 0. Okay. Recall that. So again, big and small depends on the context. Cantor set is set theoretically big and measure theoretically it is small. Okay, recall that. Cantor set I will denote by K. If I denote by C, it will get confused with this continuum C. Cantor set K. When I say Cantor set, I mean Cantor ternary set. Okay, ternary set K in 0, 1 is measurable. Is a measurable uncountable set. Oh, by the way, how do I say it is measurable?
Measure is 0.
We proved a lemma that if the
Yes.
outer measure is 0, such sets are measurable. Okay,
Yes.
it's a measurable uncountable set, and M star of K is 0. Now you consider all subsets of K. Consider subsets of K. What will be its outer measure?
Again
0.
0.
0. So will it be measurable?
Yes, sir.
Yes, sir.
So
Yes, sir.
Yes.
every subset of C is measurable. Every subset of not C, K is measurable. And therefore, you will have at least as many measurable sets as subsets of K. Right?
Yes, sir.
Consider subsets of K which are all measurable. Let me write. Which are all measurable. Recall that once it is uncountable, and it is numerically equivalent to 0, 1, and hence that of R. Recall that cardinality of K. Cardinality of K is equal to C. Do you agree?
Yes, sir. Uncountable.
Cardinality of K is C. So what is cardinality of power set of K?
2 power c.
Cardinality of power set of K.
2 power c.
Intentionally I am writing like this. That is equal to cardinality of by notation power set is denoted by 2 power K. 2 power K, that is 2 power C. And you know that power sets of K are contained in measurable sets. Because you have seen that all subsets of K are measurable, right? Since 2 power K is contained in M, cardinality of M, is it clear or what? Cardinality of M. Why 2 power K is contained in M? Because every subset
2
of
power C.
is measurable. Cardinality of M, not 2 power C, greater than or equal to 2 power C. Right, but already you know that cardinality of M is less than or equal to 2 power C. Therefore, cardinality of M is exactly equal to 2 power C. And what is cardinality of power set of R?
2 power C.
So that means they both have same cardinality. Okay. Thus, M and 2 power R have same cardinality. That doesn't mean that they are same cardinality.
Yes, sir.
You have seen examples of a sets which are in 2 power R, but which are not in M, non-measurable sets, cardinality.
Yes, sir.
So Lebesgue measurable sets and the power set have both same cardinality, namely 2 power C. Okay, that's one observation. Now give me 5 minutes. Now what about non-measurable sets? At first sight, it appears that there are only very few non-measurable sets. Every set you take, they are all measurable, and non-measurable set, we gave example with much involved work. So we feel that number of non-measurable set may be very few, but let us see. Okay. Take a non-measurable set. Existence you already guaranteed. Take a non-measurable set. From not 0, 1, but from 1 to, I think. Whatever you did on 0, 1, you can do the same thing in 1, 2. Okay, you have to define addition, modulo 2, etc., etc. Let us say A. So what is A?
A non-measurable set in
A
the
non-measurable set inside 1, 2, which you have constructed. We have constructed inside 0, 1, but why 1, 2 you will see. Now you find union of this A with each of measurable subset of Cantor set. Each subset of Cantor set is measurable, right? So let me write.
Yes,
Find union of A. Find union of A with each subset of K. I will write each subset of the Cantor set. Of the Cantor set K, which is in 0. Each subset of K is measurable. And then you are finding its union with the A.
Yes, sir.
What is your conclusion? That set will be measurable or non-measurable?
Non-measurable.
Why is it so? First of all, remember that they are disjoint. One is inside 1, 2. Here you have Cantor sets. And here you have 1, 2. Okay. So is it clear that union of A with each Cantor set, each subset of Cantor set will be non-measurable? Assume it is measurable and see what happens. Okay.
Yes.
Assume it is measurable. So I am not writing that. No. Then each of these sets, these sets I mean union of A with the subset of K is non-measurable. So like this you constructed how many non-measurable sets?
Infinite.
2 to the power.
Not only infinite, how many subset of Cantor set you can
That's
take?
it.
That many non-measurable set you got.
Yes, sir.
Okay. And what is cardinality of Cantor set?
Continuum.
Continuum. So how many subsets are there for Cantor set? 2 power continuum.
2 power continuum.
So you got 2 power continuum, non-measurable.
Non-measurable sets.
Each of these sets is non-measurable, and thus we have 2 power C number of non-measurable sets. That is cardinality of non-measurable sets. Cardinality of non-measurable sets is equal to 2 power C. And cardinality of measurable set is also 2 power C. So you cannot say there are more measurable sets than non-measurable set, or there are more non-measurable set than measurable set, nothing. Okay. In appearance, you are seeing so many measurable sets and only very few non-measurable set, maybe. That doesn't mean that there are more measurable sets and less non-measurable sets. In short, whenever you have this infinity, then you have to be careful. You have to deal this infinite cardinal very carefully. Okay. What is infinity minus infinity?
Not defined.
Not
It's
defined.
not even.
I can interpret it as infinity as well. For instance, you consider infinity to be the collection of all real numbers. Infinity I am interpreting as collection of
Yes.
all real numbers. And another infinity I am interpreting as collection of all natural numbers. And now I am taking away infinity minus infinity. Again, I will get
Infinity.
infinity. So it depends how do you want to see. And this is philosophically also Indian philosophy. I don't know whether you know this sloka. Purnamada Purnamida Purnat Purnamudachyade Purnasya Purnamadaya. If you take infinity from infinity, Purnameva Vashishyate. Again, you will get infinity. In the sense, God is complete. This world is complete. The world is given from the God. He took everything to give you the entire world, but still He is infinity. That's the exact meaning. That's the exact meaning of that sloga. But you can interpret in this cardinal sense. You have infinite cardinal. Take away infinite cardinal. Again, you have infinite cardinal. Okay. Anyway, so these are bit abstract. We are not much bothered about. Now, again, we have not, give me 2 minutes. We have not told anything about B and M.
Yes.
What is B?
Borel.
Borel set.
Borel. Smallest sigma algebra containing all
Such open set.
open set. And M is sigma algebra containing all M. And we have seen that cardinality of, allow me to write like this, okay? Cardinality of M is 2 power 6. Okay? I will leave to you to see that cardinality of B is just C. Okay? It is just C. And therefore, B is strictly contained in M. Okay? B is strictly contained in M. Later, I will give you one example of a set which is measurable, but which is not Borel set. I will give one example later. But in fact, using cardinal argument also, it is clear that B is strictly contained in M because B is having cardinality C, whereas M is having cardinality 2 power C. This I will leave to you. How to see that cardinality of B is just continuum. I will give you intuitively how it follows. What is B? Sigma algebra containing what? Open sets.
Open sets.
And in real, open sets are countable union of
Disjoint, countable,
Disjoint.
open intervals. That open intervals, if you want, you can take the endpoints to be rational.
Yes.
Yes.
So like that, the open sets are coming from countable union of countable sets. So open sets are countable. Roughly, okay, these are all some intuitive understanding. Therefore, open set, number of open sets are like countable. Now, how do you get Borel sets or Borel sigma algebra? By taking
intersection or
intersection, union, etc. When you take intersection, union, etc. of countable things, you cannot go beyond C. When you take countable things and then you combine them using union, intersection, complementation, etc., you cannot go beyond C. Maximum you can reach is C. Okay. So that is the intuition. Everything starts from countable sets and then you are taking unions, intersections, etc. Since you are taking only unions, intersection, and complementations on countable sets, you cannot go beyond the uncountability. That is C. Okay. That's the way one can understand why the cardinality of Borel set is C, but in fact it needs a rigorous proof. Okay, so that I will leave to you. And later, I will just give you one example of a Lebesgue measurable set, which is not Borel measurable. Okay, yeah. So I think with this, I will stop the business of cardinality of the sigma algebra. And next, we will go for regularity and integrability. Yes, with that, let me stop.
Thank you, sir. Have a good day.